What's up, everybody? This is Wallace from A3Academy, and today we're going to be talking about simple harmonic motion. And this video is going to specialize in sinusoidal motion, which is something that I will explain later. So, suppose that you have some object here that is undergoing simple harmonic motion, like this back and forth oscillation here. We can quantify how it is oscillating using a couple variables and equations. So, suppose you have a system that is undergoing simple harmonic oscillation, and you know the spring stiffness constant K and the mass of the object M, and you want to find out the period of the oscillation, that is, how long it takes for the oscillation to undergo one cycle, one up and down motion. You can use a simple equation. It can be found that the period t is equal to 2 pi times the square root of m over k. The derivation of this equation is kind of complicated, so I'm not going to go over it in this video, but there is a way you can derive this equation using basic algebra. Now there is another way that you can express the speed of the oscillation, and that is using frequency f. F is equal to 1 over t. So f represents how many times the spring system will undergo an oscillation in 1 second. So t is the amount of time it takes for the system to undergo one oscillation, and f is the amount of oscillations it will undergo in 1 second. Now that's simple enough. Now how do we find out where a simple harmonic oscillator is at any point in time? Well, imagine that we had an object undergoing simple harmonic oscillation. First we have it at its static position here, this equilibrium position where it is neither moving up or down, it's staying still, and then we somehow disturbed the object and caused it to move up and down in a simple harmonic motion. Now we can actually take a graph and graph where this object is as a function of time. So if we track the motion of the object over time, you'll see that a graph like this will start to form. Now this graph here is a special name, and that name is the sinusoidal curve. And any motion that is in a sinusoidal curve is known as sinusoidal motion. All simple harmonic oscillators move in a sinusoidal curve. And that sinusoidal curve can be represented with a function, say x of t. X of t is represented by the equation a cosine 2 pi t over t. A is the amplitude of the motion. Big T here, capital T, is the period of the oscillation, which we calculated earlier is 2 pi times the square root of m over k. And T is the variable where we plug in the time we want to observe to find out where the position of the simple harmonic oscillator is at a certain point in time. So now I probably just hit you with a ton of equations and a ton of concepts at one time, so it's probably best to go over an example problem. So let's get started. An 8 kilogram object on a spring with a spring stiffness constant of 1.2 newtons per meter is undergoing simple harmonic motion at an amplitude of 50 centimeters. How far is it from its equilibrium position after 5 seconds? Well, we already know some of the constants that we'll need. We know that the mass is 8 kilograms and the spring stiffness constant is 1.2 newtons per meter. We also know this equation that we can use to solve for the position at a given time. The one thing we don't know here is t, which is the period of the oscillation. To find t, we can use the equation that we discussed before, t equals 2 pi times the square root of m over k, and plugging in the mass and the spring stiffness constant that we already know, we will get that the period is equal to 16.2 seconds. Now that's simple enough. Now all we have to do is plug in all of the variables that we know into this equation. So we know our amplitude is 0.5 meters, which is the same as 50 centimeters. We know that the period is 16.2 seconds. We know that t, which is the time that we're trying to observe, is 5 seconds. And now all we have to do is solve this part of the equation, and what we'll get is that x of 5 is equal to negative 0.180 meters. And that is the same as 18 centimeters below the equilibrium position. So after 5 seconds, the object undergoing simple harmonic motion is going to be 18 centimeters below where it initially was. So that's all you really need to know about simple harmonic motion. I hope you enjoyed this video, and